I'm Professor Harald Brune, and I'm heading the laboratory for nanostructures at surfaces. We study surface-supported structures that are so small, all the way down to the size of single atoms, that their physical and chemical properties are dictated by quantum mechanics. We presently focus on quantum magnetism and quantum chemistry. The nanostructures are created by self-assembly from atoms and molecules deposited at single crystal metal surfaces and on monolayers of graphene, boronitride, and oxide thin films that are used as electron and phonon decoupling layers. Scanning tunneling microscopy, STM, is combined with spatially integrating techniques such as X-ray magnetic circular diagram, magneto-optical Kerr effect, assessing the magnetic, catalytic, and electronic properties of the ensembles of single atoms, metal organic networks, or a few atom big islands. STM itself is also used to study the magnetic excitation energies, the spin dynamics, and the coherence of magnetic quantum states. This is done on an individual atom or molecule basis. The information gained from the local probes and from integrating techniques is complementary, and combining both opens the path to the most complete understanding. This way, an atomic scale structure-property relationship is established, ultimately enabling engineering of functionality. Our most recent pioneering discovery are systems where a single atom exhibits stable magnetization, so-called single-atom magnets. These systems present the smallest possible magnetic storage unit, and some of them are candidates for future magnetic quantum bits with potentially much longer coherence times than presently known solid-state realizations of qubits. STM is a measurement technique that allows us to map the surface at the atomic scale. We can determine the structure of the substrate, the adsorption site of atoms or molecules, and the number, density, spacing, size, and shape of clusters that form. This way we can optimize the growth conditions that lead to the self-assembly of nanostructures we are aiming for. For example, we can see the individual hexagons in graphene grown on ruthenium, as well as the larger Mori pattern that occurs as a result of the lattice mismatch. Or in this image of two layers of magnesium oxide grown on silver, we can clearly see the individual oxygen atoms and the cubic shape of the lattice. STM also allows us to see individual atoms or clusters that we place on top of surfaces. Here you can see a superlattice of individual dysprosium adatoms on the surface of graphene grown on iridium. We utilize special growth techniques to achieve the uniform spacing seen. Metal clusters with a well-defined size distribution can be obtained by similar growth techniques. Conventional STMs can be modified, for example, with a magnetic tip or by injecting a constant RF voltage in the tunnel junction to extract even more information. Using these experimental techniques, our lab strives to engineer nanostructures with desired properties, such as magnetic anisotropy energy and moment, spin polarization at the Fermi level, chemical reactivity, and selectivity. The TP4 projects available in our lab imply STM analysis, applying various epitextual growth techniques, quantitative analysis of magnetization curves and spin lifetimes, statistical analysis, and the study of surface chemical reactions on a few atom-sized metal clusters acting as selective and efficient catalysts.